This video is going to address differentiation and integration of power series. The term we use for this is term-by-term differentiation and integration. So when we look at a power series, which in its most general form looks like this, a power series, it can be a function as long as it converges, because on its interval of convergence, we're plugging in a value of x and we're getting a number out because the series converges, so it's a finite number that's coming out of that infinite sum. So it's a function, and every term of that function is a polynomial. So it's integrable and differentiable on the interval for which we're getting out actual values. So as such, we should be able to find the derivative or the antiderivatives of this function, and we can do this by differentiating and integrating each term of the sum because of the fact that we know that the sum rule and the constant multiple rules are governing formulas for differentiation, and then in integration as well, we have the integral of the sum of two integrable functions is the sum of their integrals. So I'm writing down here a reminder for you of how the power rule works for differentiation and integration of a polynomial term like this. So it helps to think about it in an example. So say I had like 4 times x minus 2 to the 7th, and I wanted to take the derivative of that expression would be 4 times 7 x minus 2 to the 6th. The chain rule would ask us to then multiply by the derivative of the inside, but since the coefficient on the x is 1, the derivative of a term of the form x minus a is just 1, and so we can drop that. And so that's why you see here, since c sub n, those coefficients on the x minus a to the n term are constants with respect to the derivative. That's why they carry through in the derivative, and then we're just applying the power rule, bringing down the exponent and decreasing by 1. And because this is a polynomial expression, we're going to expect that every time we differentiate, we're going to chop off the constant terms from the power series. When it comes to integration, the integration power rule is similar. As you'll recall, the constant still carries through, so the c sub n's, those other portions of the power series that aren't powers of x, they're carrying through as multipliers. And then we divide by the reciprocal of increasing the power by 1. I'm noting that we do have that constant of integration that appears. So we do expect that if we're looking at a generic antiderivative of a function, an indefinite integral, that we'll have to account for that constant. So here is the theorem that governs this. It says that when we have a power series centered at A, and we're within the radius of convergence, then if we think of that power series as being written out in this form, then the derivative of that power series, you'll notice it drops the constant term, no constant term. So we start out with the first term coming from the coefficient on the linear term of the power series, and then from there on we're applying the power rule. So when we differentiate, key thing here is we notice that the lower index changes. Our lower index starts at 1 because the n equals 0 term corresponds to 0 now. And then when we integrate, we add a constant of integration to applying the power rule on every term. And so we get constant of integration plus the integral sum. Here the index does stay at 0 because we're actually increasing the powers of each term. And the radius of convergence will stay the same for the power series, but it turns out that frequently whether or not you've got convergence at the endpoints could change. So let's look at an example. We're going to find the power series for the function f of x equals 1 over 1 minus x, and then we're also going to find the power series for its derivative as well as its antiderivative, a generic antiderivative. So you'll recall that f of x equals 1 over 1 minus x. This is the one that I can build via the geometric series formula. So that's the sum n equals 0 to infinity of x to the n. And then to find f prime, we can either do by-term differentiation and then sort of see the power pattern, or we can go ahead and do it within the power series itself. It's worth noting that we know what the derivative of f prime of x is using rules of differentiation. We can write it for the function itself. So f prime in terms of the function itself, the original function is 1 minus x raised to the negative 1 power. So this should be negative 1 times 1 minus x to the negative 2. And then I have to multiply by negative 1. That's the derivative of the 1 minus x term itself. So we can rewrite this as 1 over 1 minus x quantity squared. But then if I do by-term differentiation, recall that the constant term, the 1 dies off, it differentiates away to 0, so we're going to start our index at 1 now, and it'll be n times x to the n minus 1. Or if we look at this series, what we're talking about is 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the fourth, and so on. Now let's do the integral. So the antiderivative of 1 over 1 minus x as a power series, centered at 0, the actual value of this particular antiderivative, this indefinite integral, should be constant of integration plus negative logarithm of absolute 1 minus x. We can do it via the power series. We're integrating, we're taking the sum, c plus the sum from 0 to infinity of the indefinite integral of x to the n. So that's c plus the sum, n equals 0 to infinity, of 1 over n plus 1 x to the n plus 1. And so we're looking at c plus x plus 1/2 x squared plus 1/3 x cubed plus 1/4 x to the fourth, etc. And so that's just a real basic example of what this looks like. Let's look at another example. This is another key way this gets utilized. So we want to find a power series for f of x equals the arctangent of 2x, centered at x equals 0. So what we're going to do to determine this is we're going to play the following game. We know that the derivative of arctangent of 2x is equal to 1 over 1 plus 2x squared times the derivative of 2x times 2. So 2 over 1 plus 2x squared, or 2 over 1 plus 4x squared. This is an expression that we could write in terms of a geometric series, and then I can integrate to get back to the arctangent. So arctan of 2x can be seen as the indefinite integral. We know arctan 2x takes value 0 at 0, so an integral from 0 to 2x of the function 2 over 1 plus 4t squared dt. So this is, I'm applying a fundamental theorem of calculus way of looking at this here. This looks really complicated. Just think of it as the antiderivative of 2 over 1 plus 4x squared, where c equals 0. And that's probably the best way to think of it. Okay? So the goal I'm going to use is, so the steps, I'm going to find a power series for 2 over 1 plus 4x squared. Then I'm going to integrate that power series. Okay, so here we go. So 2 over 4 plus 1x squared, that can be thought of as 2 times 1 plus 1 over 1 minus a minus 4x squared. And so using the geometric series structure, we're talking about 2 times the series, n equals 0 to infinity of negative 4x squared to the nth power, because negative 4x squared is playing the role of r. So we get 2 times the series, n equals 0 to infinity, negative 1 to the n times 4 to the n x to the 2n. So I distributed the part that was not related to x out, and the reason I did that is that when I integrate, this portion is a constant in terms of the integration. So let's find the integral of 2 over 1 plus 4x squared dx. That's going to be c plus 2 times sum, n equals 0 to infinity, negative 1 to the n times 4 to the n, times the exponent's going to go up to 2n plus 1, and then we'll divide by 2n plus 1. Now we know that we want the antiderivative where c is 0, because that's the way that we're going to obtain the right overall result, because we need the value of this series to be 0 when x is 0. So this implies that f of x equals arctan of 2x is equal to the series n equals 0 to infinity 2 times -4 to the n x to the 2n plus 1 over 2n plus 1. And if we wanted to look at what series we're talking about here, I've written a few terms of the series out here so you can get a feel for what it looks like and how the powers move along. The 2n plus 1 means odd powers only.